You may have noticed that many of the programs we've created so far have multiple copies of similar variables. If we're going to compare 3 cell phone rate plans, we might have double, cost 1, cost 2, cost 3. This organization is so common that Java has a mechanism to group this kind of data together, called an array. To create an array with 3 elements to store our costs, we say double square bracket costs equals new double of 3. That syntax may look a little familiar since it uses the new operator that we've used to create objects. Just as with objects, costs is a reference to the array. The memory diagram shows what this looks like in computer memory. Arrays must always consist of one type of data, so we can't have an array that contains both int and double. The name for this property is homogeneity, just like we call milk homogeneous when it's been specially mixed together so the cream can't float to the top. The other special property of arrays is they must be stored in contiguous memory locations. We showed this in the memory diagram by setting the 3 boxes for the elements next to each other. This property is troublesome in practice because it can be hard to guess how big an array should be. For example, if we're going to write a program to keep track of contacts on your cell phone, we'd have to guess how many people you would contact. For one person, 100 contacts might be enough. Another person might use 10,000 contacts. The ArrayList class hides a clever solution to this problem that you'll discover if and when you take a data structures course. The reason for the requirement that array elements be in contiguous memory is so we can find the elements in the array quickly. To explain how this works, it helps to know a little bit more about computer memory. Computer memory is like a row of numbered shoe boxes. Each box can contain 1 pair of shoes, and each box has its own address, the number written on top of it. Computer memory consists of groups of bits. The computer can set each bit to be either 0 or 1 and nothing else. Each group usually contains 32 or 64 bits and has a single address for those bits. You can think of a reference as the address of the array in memory. Suppose the first element of our array is at address 942. This means the next 2 elements will be at addresses 943 and 944. If we want to store something in the first element of the array, we say costs of 0 with square brackets equals 5.32. To put 6.41 in the second element of the array, we say costs of 1 equals 6.41. To put 4.87 in the third element of the array, we say costs of 2 equals 4.87. Notice that we use the index 0 to access the first element of the array. The array indices are shown below the array. Starting counting at 0 doesn't make much sense until you look at how the references work. To get the address of the first element, we add the index 0 to the reference costs. 0 plus 942 is 942, the address of the first element. To get the address of the second element, we add the index 1 to the reference costs. 942 plus 1 equals 943. If we try to use the index 3 for this array, we get 942 plus 3 equals 945. Address 945 is not part of the array, so we have a problem. This problem is called the array index out of bounds exception. This is a very common mistake for beginners to make. To avoid making this mistake, programmers spend a lot of time thinking about whether the first and last elements that were processed were the right ones. This is called a boundary condition. Notice that when we constructed the array, we had a 3 between the brackets, but we can't use an index of 3 because it's off the end of the array. We describe this by saying that array indices are 0 indexed and array sizes are unit indexed. 0 indexing means that the first element is 0, not 1. Unit indexing means the first element is 1. This is confusing at first, but it'll be second nature soon. Arrays are often processed using loops. Let's read the contents of a 4-element array of ints from the keyboard. Scanner keyboard equals new scanner of system in, int square brackets data equals new int of 4, int index equals 0, while index less than 4, data of index equals keyboard.nextInt, ++ index. Zero and unit indexing are the source of lots of software bugs. In fact, there's a special kind of bug that's caused by indexing confusion. It's called an off by one bug, or an OBOB. The loop below has an OBOB. Int square brackets data equals new int of 5. Notice that I'm giving you bad code here. Int count equals 1, while count less than or equal to 5. Data of count equals count ++ count. The problem is that we're setting data of 1 to data of 5 instead of data of 0 to data of 4. One rule that can help you remember this is that we usually start our index at 0 and go to less than, not less than or equal, the length of the array. We can have an array of objects too. These are stored differently since objects are stored by reference. To store an array of string builder objects, we first construct the array and then construct the string builder objects in a loop. String builder square brackets names equals new string builder of 4. Int index equals 0, while index less than 4. Names of index equals new string builder ++ index. I call this a two-level constructor, since you have to construct the array first and then construct the objects. In this case, we called 5 different constructors. If you forget to construct the objects, all of the references in the array will be null, and you'll get null pointer exceptions. The memory diagram shows what the constructed array looks like. Both the array and the string builder objects are allocated on the heap. Arrays are the first real data structure that we've encountered. Data structures is the many clever and interesting ways that computer scientists have found to store data in computer memory. The way that we organize data has a tremendous impact on how efficiently we can retrieve and use it. Data structures is a very important topic in computer science and is a really fun class that you'll be able to take once you're a more proficient programmer.